Lecture 25, Profiling, Observing Operations. If you think back to the beginning of the course, we did a quiz on operations that are fast versus operations that are slow. We found a couple of interesting things. Sometimes we're surprised. Maybe we did well individually. Maybe the class as a group didn't do so well. That sort of thing is quite common. But our intuition is frequently wrong, right? Our idea of looking at this and thinking, aha, this is fast, or thinking, oh no, I'm sure this is slow, isn't always correct. And moreover, the magnitude of the difference between the truth and what we expected can also be very large, leading us to focus on the wrong things. So, yeah. We might be able to narrow down, for example, computation of a particular task is slow, but what part? And I mean, some men just want to watch the world learn. And if we don't use tools, we end up guessing. You just make assumptions about what's slow, you try to change it, and so here now finally we're going to try to formalize this idea of measuring, this idea of identifying what parts are slow so that we can take some action based on that. And you were probably waiting for this quotation. You probably heard at least a little part of it, maybe not the whole thing, but the whole thing says programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet, we should not pass up our opportunities in that critical 3%. Okay. And as I say, you probably heard just the premature optimization is the root of all evil part of it. And certainly, this is true, and it is entirely likely that if we try to optimize too soon, we're focusing on the wrong things entirely. But we'll, for the moment, think about, well, how to measure, observe our programs. If we don't, maybe you just feel lucky, maybe you optimize the slow part, and maybe that actually does make a big difference. It can happen, and there are certainly things where they're obvious, so we don't have to spend a tremendous amount of time debating whether or not it's going to be worth our while, but that's not reliable, that's not systematic, right? If we want to make our program fast and we want to consistently be able to do that, we need a systematic and really a scientific approach. And until now, this course, admittedly is, somewhere around 2/3 of the way through in terms of lecture content, has really been about let's speed this up. Here's some different techniques, and here's some different approaches, and here's some different ways of thinking about the problem. And very little of it has been focused around the idea of, well, given that we know we have a slow part, how did we decide that, right? How did we know? How do we decide what we should speed up? So we're going to start with observation as an opening topic, and let me try to motivate a little bit the idea behind observation in the program. It's more than just measuring things. Measuring is certainly a part of it. We want to take measurements, and we want to use sort of reliable ways of gathering those measurements. But observation includes all kinds of things that are intangible, hard to quantify. We will be looking holistically at the behavior of our program, and if we notice anything, if we find something interesting, it doesn't necessarily have to be supported by a numerical, this went up by X%. So there are three kinds of observation that we are interested in talking about. There are, of course, many different ones, but there's three that we're interested in talking about right now. There's counters, profiles, and traces. And counters are, a stored count of occurrences of something, right? How many times we had a cache miss, how many times function foo was called, how many times a user has logged in over the lifetime that they've been our customer. All those things are counters, and we just add one to them as the situation requires. Profiles are higher level overviews of what the program is doing, where time is going in aggregate, and how long certain operations take. We're going to return to the subject of profiling later because it's a big topic. It's got its own discussion, and we'll discuss a few different tools while we do so about what to do with counters and profiles. But for now, we're going to focus on traces. And traces are a recording showing the sequence of events that a program is doing so we can understand the runtime behavior. You can think of it a little bit as if the trace is telling you about what is about to happen or what is happening right now or what has just happened. And it helps us understand runtime behavior. And when we look at a trace, it can help us to, trace, you see why it's called a trace, a path that got us from the start to the current state or the error state or something like that. Okay, so we're going to start our discussion of tracing with logging. And logging is, broadly speaking, an effective tool for finding out what your program is doing, like where time is going, what is important, and what is going on. We've probably all used printf or other kinds of print statements as a form of debugging. You're working on an assignment and you're not really sure why this isn't working or why it's not getting the correct answer. And by looking at that, of course, you can insert some print statements in the code, and you can run it, and you can see, foo is equal to this at this time, and x is equal to that. And at the end, you'll figure out, hopefully, something interesting. When we're running a small program, that's fine. Printf debugging does count as a valid form of tracing because it is, showing the flow of execution of your program, maybe telling you a bit about what's been called, what the values of variables are, those kinds of things. That works okay if it's a small program. It's a course assignment. You don't have that many lines of code. You don't have that much to do. But for a real deployed application, something that you're going to use in the workplace, you need something a little bit more structured than that. And for that, we're going to say that logs will need to have a timestamp, a message, and attributes. Okay, timestamp is pretty straightforward. It's just a recording of the time at which this log line was created, and timestamps are necessary for organizing and searching the logs. If you're curious about what happens on 29th of February during leap years, timestamps are helpful. Message is kind of a top-line summary. It's an idea of what is going on. So it says, I'm entering function foo, or I am configuring the configuration for company ABCD. And then you have attributes, and attributes are just different things that tell you a little bit about sort of what is happening in the systems, some variables that you might be interested in the state of, but it might also tell you which server is executing your request in case that was beneficial in diagnosing, like, hey, one of the servers is misbehaving. You could find that out by actually looking at the attributes. If you tagged as an attribute, it took place on this server. Okay, so in one of the sources that we've linked here, the book about observing systems, they say actually if you only get one tool, so we can't have any of the other things, we can't have profilers, we can't have anything else, it's logging. This is because logging can tell you a lot about how much work the software did in a given time period. It can tell you about when things are busy, when things are slow. It can tell you about when the service is down. And logging is relatively light touch. It's not very intrusive in terms of running your program. If we've talked about running your program under Valgrind or something like that, it adds a whole lot of overhead, like 100 times slowdown. In some cases, so you wouldn't want to do that on a production machine. That would probably be undesirable overall. But when we're talking about logging, the costs of doing so are generally significantly lower, to the point where, it's worth doing kind of no matter what. This also matches with our intuition. I would think that printf debugging is a good first option to figure out what's going on, maybe a little easier than running the code in the debugger, and works in some situations like we have a suspected concurrency problem where running in the debugger maybe masks the problem because just of how we are executing the code using the debugger one statement at a time. Given that we want to log, we do have to consider how often we want to log and what content should appear in the log. There's a couple of competing interests, right? This might be our only shot to get that information. If we don't put the information in the log right now, the information is lost because we no longer have, for example, a copy of the original submitted request. And if that's the case and we didn't put it in the log, well, there's only guessing about what the submitted request had been at the time it was sent in. So we don't know. For other things, though, they're kind of irrelevant. If we log too many irrelevant things, we drown out useful information, and this makes it hard to spot the stuff that we're looking for that is relevant. Logs typically have levels like error, warning, info, debug. These can make it easier to spot the information that's relevant. If we spot an error log, for example, that calls our attention to it, and maybe calls our attention to sort of what happened immediately leading up to it, and those kinds of things are more beneficial than just everything is in a flat text log with no levels. One potential approach, as an idea, is to log the input and output, so incoming requests as well as the outgoing responses, and maybe some steps in between. We're going to see this isn't magic. There are some drawbacks to this solution. There are some things about it that we maybe don't want to do, but at least at a first glance, maybe this is an interesting approach to think about, something that we could get started with. It's important that we want to be able to link different things together, so maybe we have some attributes, maybe a request is assigned a unique identifier, and the request identifier can be used to follow that request all the way through whatever process we are executing. That kind of thing is going to be helpful, again, later if we ever need to figure out what happened. So here's a made-up example that doesn't show timestamps or attributes, but if we could link all the items together that correspond to this, and these were our top-level messages, okay, we'd see received request, and then there's some log information saying, okay, we want to update the plan of company 12345 to ultimate. And then to do that, we need to retrieve the company, then we need to verify the eligibility, and they're trying to change plan here from basic to ultimate, so that's the check, that's the code that we are executing, and we will make a determination based on that company 12345 is not eligible for the upgrade due to unpaid invoices greater than 0, so evidently we don't let them update if they are owing us money. Sure, that's perfectly fine as a reason. And then we will return a response that says, okay, the request is declined. That's enough for us to figure out what happened and also to figure out why. If somebody from customer support asks you about, okay, why did this update of company 12345 failed, and they can't figure it out, well, we know the answer. And we can tell that from the logs. So we see the various steps of the process, we understand what happened, and I intentionally added a decision in this example that I made up and logged the reason for the decision, because I think that's better generally than making somebody guess why the answer was no from looking at the logs. If we can find the answer was no, but they have to sort of work out for themselves why it was no, that's not as nice of an experience in terms of tracing, debugging, trying to figure out what has actually happened. So yeah, just be mindful that someday someone, and that someone may be future you, is going to have to read through the logs to try to figure out what happened. And then there's timestamps, and choosing a timestamp strategy is actually interesting. The level of precision that you need for timestamps depends on, well, the time scale of execution. When a running process takes tens of seconds, then you probably don't mind if timestamps are down to tenth or thousandth of a second. When things run super fast, we might need microsecond or nanosecond resolution. Those kinds of things are highly application dependent. If it's anything that's sort of user interactive human timescales, then yes, we don't need anything super precise because users are slow from the perspective of the computer. But we never really know until we get there. Time zones also matter. Choosing what time zone you want to log things in, and choosing your data center defaults or your machine's defaults or something might not be ideal. And I'm going to recommend UTC. UTC, as in Universal Time Coordinated, it's GMT, but it doesn't have daylight savings time. It doesn't have other things. In fact, daylight savings time is weird when you look at logs because it can result in things going like forward, which okay, it looks like this request took 1 hour and 2 seconds when it actually took 2 seconds. It just happened to be across the barrier where the time jumped forward, but you also can have situations where time moves back in the fall, and a certain minute appears to happen more than once, which defeats our normal expectations of linear time. Time travel is cool. If you've been doing it twice a year, probably most of your life, if not all of it, depending on where you lived. But time travel is not actually as exciting as the movies make it look. With that said, it does make it actually hard to figure out sort of what is happening, and hard to choose how to schedule a recurring job. If what if 2 a.m. happens twice this weekend? We really don't want that. It also avoids fun issues where like the California team thinks it's Monday and the Singapore team thinks it's Tuesday, and you end up talking about two different things because you're referring to a thing in the logs on different actual days. With that said, I can think of a situation where UTC maybe isn't great, and that is if your application is running on a Mars rover. At that point, because it's on a different planet, the universal Earth time kind of doesn't work. So at that point, you might as well use stardates. Captain's log, stardate 46119.1. Now, listen, we've already said that logging every request might be too noisy to actually find anything in the resulting data, and the ability to search and sort is definitely helpful. It's a good start in terms of being able to manage that amount of data, but you may not wish to do that yourself. There exist log aggregation services, and their whole thing is they take in all the logs you give them and they help process them and archive them, and they can observe and report on things for you, so they're really nice. But too much detail remains to be a bit of a problem, right? So adding relevant attributes to identify what happened or to correlate knowledge makes sense. If we can see the attributes for updating plans, as in the earlier example, always take 10 times longer if the company's address is in Portugal, that's actually an interesting observation. Why Portugal? What is it about this particular country? Is it some integration with a third party for that country that causes some weird behavior? We don't know yet. But it gives us a hint, something that we could go and investigate. So that's better than not knowing that. We can take that information and at least put it in the bug ticket, even if we are ourselves not going to be the ones to resolve that particular issue. However, there is such a thing as too much information in the logs, and that is if we log personally identifiable information. Logs should always redact personally identifiable information, and this is stuff like people's names, contact information, medical records, and anything that we can think of that you really wouldn't want people to know. There exist various regulations that give a more precise and inclusive definition about personally identifiable information, so we're not going to try to repeat that here. Especially since I'm not a subject matter expert in this specifically. With that said, there are some things obviously that we know are personally identifiable information and we do not want to have in the logs. And unless the logs are really kept in secure storage with appropriate access controls, they could be seen by people who shouldn't have access to that information. And you might say, listen, they're only visible internally to our company, so it's not a problem, but that is a problem, right? Why should a developer on the website team have access to the banking details of the customer? That doesn't make sense. My opinion is that they shouldn't, and it's not just my opinion, but it's also the opinion of people like the Privacy Commissioner of Canada, and you probably don't want to anger that person. That's just my guess. And one of the situations that I've observed that can potentially lead to overlogging, that is, putting too much stuff into logs, things that doesn't belong there, is that it's too difficult to get information in other ways. And this is a fun situation in which security policy actually makes things less secure. If it was difficult or impossible to use other tools or to get read access to the database to try to figure out what's going on, if somebody is trying to debug certain behavior of the program, they might put way too much stuff into the logs because that's the only way to actually trace what's happening. And if you do that, of course, again, you're risking angering the privacy commissioner, which we would prefer not to do. But it's frustrating. So we're aiming for a balance, right? We want to include the relevant information that would let us spot patterns, let us correlate any useful observations, things that we otherwise might not have noticed, but not so much that we're drowning out important information, and certainly not putting personally identifiable information into the logs. There is a third way that we could actually log too much, and that would be if the overhead from logging or from tracing in general is very significant. Normally we're typically accepting a small slowdown in our program to have some amount of traceability, but let's actually sort of put some numbers to the figures here. And if we look at the notes, the source for this is cited for this particular topic. And yeah, what we'll observe is for CPU trace tools to track, say, every conditional branch that's taken, that tends to result in about 20 times slowdown. This amount of overhead is probably acceptable if we are debugging ourselves, using our own laptop, or in a test deployment where it's not actually serving live customer data. Something like that, that might actually be a reasonable amount of slowdown, but certainly we wouldn't accept that in a production environment. That would be way too much, and users would notice and users would complain. So we don't want that. If we ask for a timestamp on every function call and every function return in our program, the slowdown is 1.2 to 1.5 times slowdown. This may, emphasis on may, be acceptable in a production environment if the task is not time critical, but only temporarily while we are experimenting or otherwise observing the behavior of our program, try to figure out what it's doing. Third option, if we ask for a timestamp of every system call, enter and exit, this is user space to kernel, transition, and return, that might be much less than 1% overhead. That's probably acceptable in a production environment for anything but the most time critical of operations, and that's the kind of thing you could leave running all the time, unless it was truly make or break performance critical, which probably it isn't, but it could remain in place otherwise. Now, the other overhead tracing covers things that are more than CPU. We'll talk about CPU tracing much more in an upcoming topic, but what about other stuff? Memory. Well, if you've used Valgrind, and I mentioned this already, you know about this. Valgrind runs your program under the supervision of itself, and the target program runs much slower, something like 100 times slower, but you get a lot of additional checks and a lot of monitoring of the program. Why is Valgrind so slow? Well, it checks every memory read and every write for validity. Is the variable initialized? Is it past the end of an array? All kinds of fun things that we, I won't say no longer have to think about, but at least rarely have to think about in Rust. But it also spends a lot of time recording information about where memory is allocated, trying to help programmers track it down. So if there is a memory leak, we can find the genesis of it. All of those things so that it can appear in a nice stack trace where it tells you at the end, this is how we got to this location. So there's a lot of work to be done. It's neat. It's a great tool. I think students who write C code in ECE 252 find it to be very helpful, and I know it's to be pretty common in other situations as well, but it's expensive. Meanwhile, disk trace tool, it would have relatively minimal overhead. Disk is very slow in comparison to the normal execution of the program, so adding a little bit of extra overhead, recording disk accesses is small in comparison to the time it takes to actually fetch the data from disk or write the data to disk or something like that. There are also uses for traces in terms of identifying locks, identifying deadlocks, and waiting for locks and what have you. And you could potentially identify it just by putting in some logging that says I want to log every lock and unlock. And that would get the job done. It would give you some information about what the threads are doing and when they're acquiring locks and when they're releasing them. That, however, might be drowning out the information that we actually want with stuff that we don't need. Why? Because we only really care about locks that have contention. And locks that have contention is just another way of saying locks that are used by multiple threads and there's fighting over them and waiting for them. Threads failing to acquire a lock because another thread is holding it. If our intention is really to observe the behavior of the program to identify what's going wrong, situations where we acquire the lock immediately are not actually what we're looking for, because there's no delay there, right? One of the things that we expect of a semaphore, and again we would have covered this in ECE 252 or an equivalent course, is that if the lock is unlocked, then we shouldn't get delayed in entering the critical section. So we should have nothing to do when it comes to a lock that is not contended. And then space, the final frontier. Yes, another Star Trek joke. Whatever trace strategy we choose, the trace itself actually takes up space. And this is another reason that we need to be a little bit judicious about what we're going to include in the trace information. If we're producing a large amount of data, it obviously won't all fit in memory. That's fine. And some of it will have to go on disk. Okay. But it's possible that the amount of data that we are going to produce fills up the disk very, very quickly. Or at least arrives so fast that the disk cannot keep up. There's a quick calculation in the source here that says if we have a main memory system with 20 gigabytes per second bandwidth and 64 byte cache lines that records up to 8 bytes of data per trace entry, that could produce data at a rate of 2.4 gigabytes per second. That's a pretty overwhelming amount of data. Even if you can write it out to disk fast enough, that fills up an 8 terabyte hard drive in just under an hour. So yeah, that's pretty extreme when it comes to how much data we would end up recording. We should aim certainly to record a little bit less than that just to keep things more manageable. But it gives you an idea of the scale of the problem and why we have to be judicious about the amount of data that we are going to capture.